Hello everyone, this is Satvik and I will be presenting the Tier 1 today from our team. Our team is focusing on Eclipse attacks. Firstly, a quick recap of Eclipse attack. Eclipse attack is simply an attack which completely or partially eclipses the victim node. Eclipse attack happens in peer-to-peer or P2P network layer. P2P layer contains mainly the node connections and its corresponding protocols. Through Eclipse attack, hacker can create inconsistencies in the blockchain network and thus can easily trigger a lethal attack like 51% attack, double spend attack, stubborn mining attack. The main goal is to hijack routing table of the victim node. Last 2 weeks, we focused on a particular Eclipse attack called false friends attack. We'll be presenting this particular attack today. Before going to the attack, first we will discuss the Dev P2P architecture. Dev P2P is a session management module in Geth inside the P2P network layer. Architecture in latest Geth version is as follows. Every node by default has 25 TCP connections to other peers. Of 25, 17 are inbound connections which are initiated by other peers. Inbound connections have no restrictions other than TCP protocol, which means once the inbound slot is available, Geth imposes no restrictions for other peers to fill the inbound connections other than the TCP or a generic Ethereum protocol restriction. So attacker can easily attack victim nodes inbound connections. Remaining 8 are outbound connections, which are important for the attacker to eclipse the victim node completely. So we need to focus on outbound connections because it is a very important for the attacker. Dev P2P, which is a session management module, sets out outbound connections from two routing tables, namely discovery table and the lookup table. We'll go through how both these tables filled and how this works. Before that, let's take a look at this figure. So this figure presents how Dev P2P sets the outbound connections from these two tables if n slots are empty. So there is a variable called floor of n by 2 and this will be calculated, and as per this Dev P2P will take the fillings from both these tables. So how DST table fillings works? DST has a k bucket storing system which is inspired from Kademli algorithm. Peer nodes are stored in the respective k buckets based on log distance metric. K bucket 255 means distance between the local node and the peer node is 255, which is the common prefix of the hashed node ID. And peer node with common prefix 255 will be stored in the k bucket 255. So so coming to how the DHT table fillings works. Whenever data is received by an inbound node or by any circumstances like unsolicited ping or pong from the peer node, Dev P2P stores this node in the respective K bucket as per the storing system. And this figure presents uh, how the actual storing works. Like there is a replacement list, which when that corresponding K bucket is full will be placed in the replacement list. One more thing to note, Dev P2P requires the last node in every K bucket every 5 seconds. If this node doesn't respond, then the last node in the K bucket is removed and the replacement list node is added. So how the lookup table works? Lookup algorithm sends a find node request to a desired node T randomly selected, Now the node T returns a set N naught which contains 16 closest peers in its DHT. Now lookup table or algorithm queries with find node request to all 16 nodes present in the set N naught. Now all 16 nodes returns with their individual sets. Now we create N1 which is equal to N naught union all these sets. And then we prune this N1 so that it contains only 16 closed pairs. If N1 is not equal to N naught, then we go to step 3 after equating N naught to N1 and then start step 3, step 4. And then this loop will end only when N1 equal to N naught. And once N1 equal to N naught, the 16 closed pairs will be stored in the lookup table. Now coming to false friends attack. So false friends attack is a low resource Eclipse attack which attacks the long running victim nodes. So we don't want we don't need the victim nodes to restart. We This attack can easily attack the long running victim nodes. So what are the exploitations? Uh, so this attack will exploit 5 facts. Number one, uh, the fact that node IDs are SHA-256 hashed ECDSA pair generation. Uh, we can easily generate 35,000 pairs per second, and thus this can be a very weak one to attack. Uh, Number two, DHT table filled nodes can be replaced every 5 seconds if the node did not respond. So this is one more weak link. Number three, storing in DHT table is by log distance metric, uh, which is the K bucket storing system. And number four is we attack the function read random nodes property and sorting property of DST table K bucket. Uh, so this is very specific to how get actually invokes the functions. Uh, Number five is we attack through lookup table protocol. We will do pre-computation of the nodes and attack this lookup table. We will see how these exploitations work in DHT and lookup table. Coming to DHT table exploitations, the attacker will try to set one adversary node in each K bucket in DHT table. Uh, as you can see, if attacker puts one adversary in every K0 bucket, he can then do continuous ping pong to make this bump to the header of the K buckets. Then invoke the function read random nodes of dev P2P protocol. This will surely pick uh, the adversaries as the outbound connections. Currently, Get supports only 239 to 255K bucket. So by computing the average, we see we require 262,000 pairs of generations or the node IDs to successfully attack the DST table. And this is very uh, quick because we can generate 35,000 pairs per second. Coming to how the attacker exploits the lookup table. Remember, lookup table pick the nodes of DST table of randomly selected node. So if lookup algorithm selects an attacker node or a victim node in the blockchain network, then lookup table can be hijacked. This one is difficult for the attacker, but once the algorithm selects the target node, which is under attacker's influence, then attacker uh, will surely uh, make a very lethal one. Once the uh, lookup table selects the attacker influence node, he will start generating the pairs. through pre-computation. Uh, by calculating, we see that we require 5 million node IDs to hijack the lookup buffer. So this equals 2.5 minutes using 4 parallel thread processor, uh, or we can also do with 11 minute with a single thread processor. Attacker has some IP restrictions to perform this attack. Surely there's an impact due to these restrictions. In an experiment, the false friend attack was successful after around 4.7 days or 114 hours. As you can see, this is a very uh, 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 relevant attack to check. Coming to uh, uh, our implementations, we actually uh, read the get code and generated a signaling plot using MSC generator. Uh, you can see a server, which is a dev P2P module, uh, gives a setup discovery uh, call to discovery module, and then after finding the node, a relevant node from its peers, the DST table will get updated. Similarly, we have the lookup algorithm happening with the function find node request. So this is a very nice table to look up and work on in future. Now coming to our Python implementation, we are trying to implement this attack in Python. We already created multiple instances or pairs with all DBs that are there in Get. Uh, we also filled the DBs using JSON file. So we are uh, at the right time to perform this attack now. So these are our coding glimpses in the Python. So these are two JSON files that we created, and these are all files that we coded in. So there is a lookup.py where lookup algorithm is coded in, discovery file, db file, server start, which is dev P2P management module. Uh, in addition to the Python implementation, we also implemented a greenfield uh, blockchain network in our language. We created a blockchain with proof of work module and mining module in K language. This is purely a greenfield implementation, and our goal is to build a blockchain network for our applications. So uh, coming to solutions, we want to explore machine learning ideas to reduce the impact of Eclipse attack, especially false friends attack. We also want to explore queuing theory ideas, mainly studying its routing algorithms. We also want to explore other ideas presented in various research papers like immune architecture design, uh, for intrusion detection system, etc. We want to explore algorithms in more broader areas and apply to this false friends attack to negate it. If you have any queries, please feel free to contact me. Thank you for listening.